Welcome back after lunch, everyone. We have two talks in this session before the tea break, 2.5 an hour talks. And the first one is by Veronique Dansereau. Sorry for pronouncing your name probably in a very, very wrong way. She will be talking about new continuum rheological model for the drift and deformation of CI.
Thank you. Okay, so I'll be talking about this new model that we've been developing. It's been a few years now. So as some of you already know, we developed this model and we base our approach on previous observational studies which have analyzed sea ice deformation, either from RGPS or ice buoy data. And these statistical analyses have highlighted three important properties of sea ice deformation, which are the anisotropy, heterogeneity, and intermittency. And even more importantly, these studies have shown that the deformation of sea ice is more heterogeneous and more intermittent than the forcing acting on the sea ice, which means that these properties come from the mechanical behavior of sea ice itself, not from the forcing. And we all know that these properties translate into temporal scaling, spatial and temporal scaling laws, which are the signature of two types of mechanisms that occur in the sea ice. So first of all, as Agnieszka mentioned this morning, so there is brittle fracturing going on. More specifically, there is an accumulation at multiscale of episodic brittle fracturing event, and also to allow for some local brittle fracturing event to trigger much larger event and to translate into deformation patterns that are correlated on much larger space scales. You need to have some long-range interactions going on in the sea ice cover. But this brittle deformation is not the only process going on in the sea ice cover. Otherwise, modeling life would be much easier. There's also another process going on, and in particular, there are also larger and much larger and permanent deformation that occur once the sea ice is fractured, leads open, and ice flows start moving relative to each other, which sets the overall drift pattern of the sea ice. So we believe that the suitable model for sea ice must allow to represent the brittle fracturing processes that lead to the extreme localization in both space and time of the deformation, and also it needs to allow for a transition between the small brittle fracturing processes and the much larger permanent deformation that occurs once the ice is fractured. A couple of years back, there was a model that was suggested to better represent the brittle fracturing processes within the sea ice cover, and that's the elasto-brittle model that was initially developed for rocks. So this model is represented here. The constitutive law is linear elastic, which is represented here by the spring, and it includes a progressive damage mechanism by which the elastic modulus of sea ice is allowed to be degraded as soon as stresses become overcritical and damage occurs. It means fracturing occur in the sea ice cover. So in this framework, elastic interaction plays a role of long-range interaction in the spatial domain. But there is a very fundamental intrinsic limitation to this model which comes from the constitutive relationship itself, and it is the fact that the model is strictly elastic, which means that it doesn't make any difference between the elastic deformation and the part of the deformation that might become permanent due to the damaging of the spring. So that means that if you're loading the system, so you have an initially elastic behavior, and you have going to be a departure from this behavior due to the fact that you have damaging, but the model only solves for the elastic deformation. So strictly speaking, if you unload this system, what happens is it goes back to its initial position. So basically, there's no movement going on. So you can still use this model, but it will be restricted to very short-term simulation. So that was the case, for instance, in the first implementation of this model on the scale of the Arctic by Lucas Gérard. So you had only a 3-day simulation, so no advection going on. If you want to use this model in long-term simulation, and so accounting for advection processes, you need to make some assumptions. So the most basic assumption you can make is to integrate permanent deformation step, which means that after loading the system, you basically freeze all the deformation and assume it's all permanent. And doing that, you might justify your choice based on the fact that in the ice pack, the elastic deformation are much smaller than the large permanent deformation that arise once the pack is fractured. So this was done actually in the second implementation of the EB model on the scale of the Arctic, and it showed to be still able to reproduce some spatial localization of the deformation. However, this is only one part of the good answer, because doing this, what you do is that at every loading time step in the model, you dissipate all of the applied stress, which means that you erase at each time the memory of previous stresses. And as I will show you in an example in the next few slides, doing this, you're not able to represent one of the important characteristics of sea ice deformation, which is its intermittency, or what we call extreme localization in space. So a suitable model must actually allow for the fact that the right answer is in between here. So you have part of the stress that you need to keep into memory and part of the stress that needs to be dissipated in the large permanent deformations. So we built a model. Actually, it was based on this elastobrittle model, and the goal was to overcome this limitation and have a model that could be used in long-term simulation for sea ice, and which will still have the capability to represent intermittency and heterogeneity. So I will describe this model today and all of his components. I'll start by showing some idealized simulation, and I'll present briefly a first implementation of the model on geophysical scales. After that, I'll talk briefly about recent implementation in sea ice models. So, as I said, we wanted to build a model that's capable of partitioning between the part of the deformation that will be elastic and part of the deformation that will become permanent. So we turned to rheology that's capable of doing just that, and that's the Maxwell model, and it's represented here. So it combines a linear elastic constitutive law with a linear viscous component that's represented by the dash plot here. So what happens when you apply a stress on the system? Initially, well, as instantaneously, all the deformation is going to be taken up by the spring, but if you wait some time, delta t, some deformation of the dash plot is going to happen, and this deformation is going to be permanent even if you unload the system. So this system can be written in this constitutive law here, and it is expressed in terms of the total strain rate, not strain. So one advantage is that drift velocities are defined naturally. So here you have the elastic term, and here is what we call the relaxation term for the stress. And one very important point is that the viscosity here is not the true viscosity of sea ice, because it's very high. So if it was, we would need to wait a very long time for permanent deformation to be large. Instead, it's what we call an apparent viscosity, and it represents the mean resistance of the ice to flow. Actually, it's a concept that we borrowed from some modeling approaches of lithospheric faulting, which have the same problem as us, which they need to represent large and permanent deformations. And actually, there's a more interesting way to write this constitutive law, which involves actually the ratio of the viscosity and the elastic modulus, and that ratio has the dimension of a relaxation time and expresses the capability of the system to keep the memory of stresses. One very important feature of the Maxwell EB model is that all of the mechanical parameters, so viscosity, elastic modulus, and relaxation time, they're not constant, but they're coupled to the level of fracturing of the ice, which we call the level of damage, and represented by a scalar variable d, which evolves between 0 for a completely damaged and 1 for an undamaged material. And the coupling is as follows. So for an undamaged ice cover, the elastic modulus is the elastic modulus of undamaged sea ice, and the viscosity and relaxation time are very, very large, so that this term in the equation actually drops out, and we don't have unphysical viscous dissipation over undamaged ice. We recover an elastic, linear elastic relationship. Conversely, over damaged areas, all parameters are allowed to decrease. So what's going to happen is you're going to have large deformation, and because the relaxation time itself decreases, these large deformations can become permanent. For the coupling with the level of damage, we seek the simplest solution. So as in other progressive damage model, the elastic modulus is directly proportional to the level of damage. And to account for the fact that we want the relaxation time to decrease with damaging, we introduce this little parameter, the exponent alpha, which needs to be greater than 1 in the relation of the viscosity to the level of damage. On top of that, the mechanical parameters are coupled to ice concentration to account for the fact, for instance, that where ice concentration drops, the model is actually going in a state of free drift. And in this case, the form of the dependence we took from the formulation of the ice strength in compression that was suggested by Hibbeler. Okay, so the damage criteria in our model is actually based on in-situ stress measurement. So it's a combination of a Mohr Coulomb and a tensile strength criteria. Both criteria are a function of a mechanical parameter which we call the ice strength, the ice cohesion. And we introduce an important ingredient via this damage criteria, which is disorder. We introduce it via the field of cohesion, and this disorder represents all sorts of natural heterogeneity in sea ice, which happen at all scales. So it could be leads, it could be thermal cracks, brown pockets, and it goes down to micro scale. We have ice crystals. So since these heterogeneities have a spatial scale that's naturally much smaller than the smallest available scale in our model, which is the spatial resolution, we actually introduce noise at the scale of the model element by drawing this value of cohesion from randomly from a uniform distribution that spans measured values. So what's happening if we apply a stress on this discretized piece of ice here? So the weakest element, the element with the smallest cohesion, is going to fail first. So its level of damage is going to decrease beyond the value of 1. And in the Maxwell EB model, this decrease is actually calculated exactly as the distance between the state of stress of the overcritical element and its damage criteria, which we call distance criteria decrit. And so because this element is damaged, mechanical properties are degraded. So at the next time step, the element is embedded in an elastic matrix. So the extra stress that it cannot withstand is going to be transferred to the nearest neighbors, which can in turn become overcritical. And because of a succession of elastic interaction, damage can propagate over a very large distance in this model. And what we do is that we associate a time to the redistribution of the stress in between elements, and we consider that this time is upper bounded by the speed of propagation of elastic wave in the media, which carry the damage information. So we have a characteristic time for damage, which is just the ratio of the spatial resolution and the speed of propagation of elastic waves. And for a model resolution of 10 kilometers to approximately 100 kilometers, this time is on the order of tens to a few tens of seconds. And using this characteristic time, we can express this progressive damage mechanism via a continuous equation for the level of damage D. On top of that, we add a recovery mechanism for the ice to recover its mechanical strength. And in the case of sea ice, that represents the refreezing of ice between open leads. And that allows the level of damage to increase from 0 back to the undamaged value of 1. And there is a characteristic time to this process also, which would depend in a coupled model on the temperature of the air above and the ocean below. In the simulation I'm going to present here, we consider this time constant because we're not coupled. So we have a constant rate of healing. And although this process operates on timescales that are much larger than damaging, the two processes operate simultaneously, so they're combined in a single evolution equation for the level of damage here. And finally, we impose mass conservation as in previous sea ice model. That's done through conservation equation for the ice thickness and concentration. So in our case, we consider a very simple redistribution scheme. So the thickness is the sum of zero thickness ice, open water, and H thick, which represents the mean thickness of the ice-covered portion of the ice, of a grid cell. So we have a conservation equation for the ice concentration, and the redistribution scheme works as follows. So if, as a result of converging motion at any time step, the ice concentration becomes greater than 1 over an ice element, what happens is that we use this extra ice concentration to update, to increase the ice thickness over that element. So it's basically just conserving ice volume. Okay, so this is the model in a nutshell. So we need to add to that a momentum equation, which is the basic momentum equation for sea ice. And that's the mechanical part of the model. So I present to you a constitutive relationship, the failure criteria, and the progressive damage and the healing mechanism. And what's important is that we included these ingredients in the model. So we have long-range interaction that come from the elastic part, a dissipation mechanism for the stress, some disorder, a threshold mechanism, and a recovery mechanism. And we added mass conservation and transport equation. And we are solving that using finite elements and variational methods. The model uses a Eulerian scheme, and I implemented Galerkin discontinuous method to handle advection. And there's also nonlinear terms that arise from the objective time derivative of the stress tensor here that we need to take into account. I chose these methods basically for the fact that they're known to be little diffusive for polynomial approximation of or greater than 0. Okay, so what I want to do first is present you some very simple test case that are going to give you a feel for what the model can do when implementing elastic interaction, a threshold mechanism, and some viscous dissipation of the stress. So here, the experiment is a compressive uniaxial compression experiment of a 2D plate of ice. There's no advection going on, it's only small deformation. Plane stresses are assumed, and we're compressing the ice plate by applying a constant velocity on the top and holding the bottom part fixed in the vertical direction. We start from an initially undamaged plate, and here what you see on the left is the level of damage of the plate, and here is the order of magnitude of the ice deformation. With here, you're going to have the stress integrated on the top boundary, and here the damage rate in blue. Okay. So what you see is that there are very sharp drops of stress that are accompanied with very high rise of the level damage that correspond to the propagation of a macroscopic rupture. And so we have cycles of healing, which increase the stress, and damaging with a very sharp drop in the stress. And at every cycle, the model reproduces a linear feature that has a different geometry and different orientation. And the deformation within that fault, that fracture, is order of magnitudes higher than over the undamaged part of the ice, of the plate. So we already get a very complex behavior, and what's very important to take away as a message from these simple experiments is that this complex behavior doesn't come from the forcing itself, because it's very simple and it's homogeneous. So it really comes from the mechanical behavior of the model. And we can analyze the output of these models either on the point of view of damage or a point of view of deformation. And since we've been talking a lot about deformation, let's talk today about damage. So here is a typical field of damage, and we can analyze it in space using a correlation integral, which is just the probability of any two damage events to be separated by a distance r. And this correlation integral is expected for a fractal population to scale with this distance r and with an exponent d that represents the correlation dimension. So 1 means that you have localization along a linear feature, and 2 means you have a diffuse distribution of damage. So if we look at this field here, which happens directly after a macro rupture, it is no surprise that we get deformation damage that is actually localized along a linear feature. And if you look at this field over a larger time period, so integrated in time, you start losing this localization because of the fact that you are superposing different fracture events with different size and orientation. So this is a signature of a space-time coupling in some sense. Conversely, we can also analyze this model based on time. So we can analyze the damage rate time series. So here is the power spectrum of that time series. So it's expected to scale with the frequency f and an exponent is greater than 0, with 2 representing damage rate that is correlated in time. And what we find is that we actually have a correlation at all time scales between the time of healing that we prescribe in our model and the time of propagation of the macro rupture. So this is a strong signature of the intermittency that we're reproducing. Okay, so now I would just want to say a few words about intermittency, and just to illustrate what I was talking about in the introduction, which is if you have a purely elastic brittle model and you freeze its deformation after each time step, you don't get intermittency. And in our model, there is a very nice way to do that. We can switch between different behaviors by varying the value of this exponent alpha, which is maybe the only truly fudge factor that we have, is the least constraint parameter. And we can vary its value between greater than 1, which we know we need to have a relaxation at time that decreases with damaging, and very high values. And in that case, we actually retrieve the situation that I was talking about, that is an elastic brittle situation where you would actually freeze all the deformation at the end of each loading time step, and actually you are losing the memory of stresses at the onset of damaging. So what happens when you do that? This is the same type of simulation. That's uniaxial compression. There. And what you get is a very trivial response. So now you still have cyclic loading and unloading of the system, but at every cycle, the system kind of forgets of what it was doing before, and it reproduces always the same feature. So what's important to take away from that is that, of course, if you would put some more complex forcing on that system, it would be able to represent the formation of different features with different sizes, different orientation, and with some intermittency. But in that case, the intermittency would come from the forcing itself, not from the model. So if you analyze this signal, it is no surprise that what you get is a loss of the intermittency. Actually, you see only one characteristic frequency that corresponds to the healing time we're prescribing in the system. And not only that, another important point is that because time and space are always coupled in these kind of systems, if you're doing that, you also are starting to lose some spatial localization, starting at the smallest space scale. So in brief, the conclusion from these experiments is that if we want to represent the level of complexity we want in the deformation of sea ice, we need to include a partial dissipation mechanism for the stress. In our case, we do that by using a damage-dependent relaxation time. Okay, so now I'll just go briefly over first just implementation of that model on geophysical scale, and for that we chose a test case, which is the drift of ice within a narrow channel. So you have here Nair Strait. It was an interesting case for us because of the mechanical behavior of ice when it drifts through a narrow passage. Tends to form these concave ice bridges that can stop the flow of ice for several months. So here's my simulation setup in this case. So we are solving the full momentum equation. We're prescribing no slip condition at the coast. The ocean is at rest, but we have a passive drag underneath, and we're prescribing uniform northerly winds that are increased from 0 to 1 Newton per meter square in 24 hours to simulate the passage of a storm and the orographic channeling of the winds between Ellesmere Island and Greenland here. We're starting from a non-damaged sea ice cover. And here's what we get. So on the left is the level of damage. Oh, you don't see the contours, but anyways. And here is the ice concentration. So you see that we are forming some arch-like leads. And eventually, there is a stabilized bridge that formed here between Kane Basin and Smith Sound, Kane Basin and Smith Sound. Okay, and once the ice detached from that bridge and it's flushed out of the channel, so we're able to reproduce arch-like leads, ice bridges, as I said. There's also, you can see it because you don't see the contours, but the model is able to represent stable fast ice. You have to trust me on this one. But there is fast ice here and here and here. Okay. I'll skip that because I want to show you other stuff. But we were also got interested into the ice thickness distribution. So as I said earlier, we're using the simplest possible redistribution scheme. just to see the input of the rheology on thickness redistribution, and we're interested in reproducing the exponential tail of the distribution that translates the fact that the thickest ice is highly localized in space. So if you plot typical sea ice distribution of a semi-log plot, you usually have a linear tail here. So this is the same simulation now showing you sea ice thickness. And here you have the distribution for different times with the warm color representing the later time. And you see that for all times, we actually are able to reproduce this exponential tail of the distribution, which we think is because the model reproduces the extreme localization of ice deformation, simply. Okay, so this just gave you a flavor of what the model is able to do. And what's even more exciting now is that this rheology is now implemented in 2 different sea ice models. So the first one is NEMO-LIM 3. So this is a Eulerian finite difference model, and it's a coupled sea ice ocean model that's going to give us the possibility to evaluate the impact of the rheology on the dynamics and, more importantly, on the thermodynamics of the model. In this framework, there are 2 rheologies available at the time, so EVP and Maxwell-EB. And so Jonathan Rollier, who's a PhD student at UCL in Louvain-la-Neuve, is analyzing the simulated deformation at the time in the Maxwell-EB model. And I invite you to go see his poster about that. And the rest of his work will be concentrating on what is the impact of the rheology on the simulated heat and salt flux in this model. So, this is an example of sea ice deformation from that model, including the Maxwell-EB rheology. Okay, and the second model is NEXIM, which is developed at NERSC by the Pierre Ampal's team. So this is a Lagrangian finite element sea ice model, which resolves wave ice interaction. So we have regional and high resolution global Arctic configuration, and there's 2 rheologies available, so original EB and Maxwell-EB. And they are analyzing also the simulated deformation with validation against RGPS data, and also the simulated heat and salt flux in this model. So there are 2 papers that are soon to be submitted about that. And I'm just going to show you an animation with this model. So this is started from ISAT ice thickness field. So this is framed straight over 3 days. Oops, sorry. How can I do that? What? Okay. So this is the ice thickness. That's represented here. And as I said, they are also analyzing heat fluxes. So I'll show you this on the big screen. Up. No. No. Ah. Okay. So this is oceanic heat fluxes. So this is a 1-year simulation that is forced with realistic reanalysis wind and ocean forcing. So what you see is actually that, heat flux are highly localized with this model. And what strikes me is that it's highly localized, and it's not even very high resolution. Here we have only a 10 kilometers model resolution that gives you very localized heat fluxes. Okay, so to conclude, so we've developed a new rheological model, a continuum model for sea ice, which includes all these ingredients. And the most important contribution compared to previous version is the addition of a dissipation mechanism for the stress, which gives us a way to allow a transition between the small brittle deformation of the ice pack and the much larger permanent deformation that occurs once the pack is fractured. And it also allows us to represent this time the 3 important properties of sea ice deformation, which are anisotropy, heterogeneity, and intermittency. Okay, so I am still working on some additions to the rheology. For instance, on the validation of these parameterization for the dependence of the mechanical parameter on level of damage and ice concentration. But the bulk of the model is already ready for use. And the fact that it's implemented in 2 sea ice models will give us a way to compare it with actual observation over the Arctic, and also to make intercomparison between these models. And so there are studies, papers coming soon. So so I'll leave you on that. Okay, questions?
kind of a question and a comment. Your apparent viscosity, is
Yeah.
that something that you compute based on the characteristics of the flows and the whole system? Or is it a fitting parameter or something? And I kind of point this out.
Yeah,
Because, because Einstein actually worked on the effective viscosity of like a dilute suspension of spheres and so
Yeah,
on. But
yeah.
even Einstein was only able to get the first term in a Taylor expansion.
Yeah.
And so this is a tough problem, but I was curious.
Yeah, but the answer is, so when we developed the model, it was really a parameter, so need for zero damage, it's actually infinite, well, in the computational sense, it's the highest value you can get.
Yeah.
And then we couple it to damage, so it just decreases as a function of damage, in the model. But now what we're doing actually to validate this approach, so the dependence of the viscosity I have on D and this with this exponent alpha, what we're doing is actually we're looking at D&amp simulation in which no viscosity is prescribed at all, and we're able to calculate a viscosity of the macroscopic scale in the system and see how that viscosity evolves with damage. And preliminary
Numerically you're evaluating.
Exactly, numerically. And the preliminary result is that the dependence that we sort of, guessed as we used as a first guess, actually is reproduced in these D&amp models. So I actually will be maybe talking about that at the fourth workshop. That's work in progress. Yes.
Great.
Yeah.
Okay, we have time for